Okay, let's start today's seminar. Today's speaker is Masanori Tanaka from Osaka University. He will talk about proving first order electroweak phase transition via PBHs in the effective phase theory. Let's start when you're ready.
So thank you very much for the introduction, and thank you very much for giving me the opportunity to talk about our research. So today, I'd like to talk about the relation between the electroweak phase transition and a primordial black hole by using the new effective field theory. So I'm a postdoc in Osaka University. So from September, I will move to the Peking University as a postdoc. So this work is based on the collaboration work with Professor Shinya Kanemura in Osaka University and Professor Tomo Takahashi in Saga University, and the Dr. Katsuya Hashino in Fukushima College. Okay, so let's start the introduction. So as well known, the standard model in particle physics is really consistent with further experiments like the LHC. So, however, the standard model has a severe unsolved problem, like the variation symmetry of the universe and the existence of dark matter and the origin of tiny neutron masses. So, in order to solve this problem, it is well known that the dynamics of the electroweak phase transition can play an important role. So, therefore, exploring the dynamics of the electroweak symmetry breaking or electroweak phase transition is very important. For example, in the electroweak baryogenesis, this which is a promising scenario to explain the barrier symmetry. This mechanism requires a strong first order electroweak phase transition. So in the later, I will explain what is electroweak baryogenesis. So we have a naive question. The naive question is, how can we test the first order electroweak phase transition? So there are three options. The first one is a precise measurement of the triple Higgs boson coupling at a future quadratic experiment. And the second one is an observation of the gravitational waves produced by the first order electroweak phase transition. And then there's a new way to explore the first order electroweak phase transition. The new way is that the primordial black hole observation. So in this talk, I'd like to explain the relation between the primordial black hole and the electroweak phase transition. So next, I'd like to talk about the baryogenesis and the electroweak phase transition. So as well known, the baryon symmetry of the universe is observed by C cosmic microwave background and Big Bang nucleosynthesis. So this is the observed value of the baryon symmetry. So the NB is a baryon number density in our universe, and N gamma is a photon number density in our universe. So in order to explain this value, so we need a mechanism which satisfies the Sakharov's condition. So this is the Sakharov's condition, and the first one is a baryon number violating process. And the second one is a C and CP violation. And the third one is a non-thermal equilibrium. So although the standard model can satisfy the Sakharov's condition, however, the observed NB cannot be explained. So as I mentioned, the standard model may be able to satisfy the Sakharov's condition. And the first condition is satisfied by the Smadron process, so which is the baryon number violating process. And the second one is a CP phase in the Kabi-Bokobayashi mass cavity. And the non-thermal equilibrium situation is realized by the first order electroweak phase transition. However, unfortunately, the electroweak phase transition in the standard model is a crossover and not a first order. Therefore, this third condition cannot be satisfied in the standard model. So even if we neglect the third condition, But however, the CP variation in the CKM phase is too small to explain the observed baryon symmetry. So this is a typical prediction in the standard model. So the NB is, the eta B is a prediction of the standard. And as we can see, so the prediction in the standard model is around 10 to the minus 22. So this value is very small when we compare the observed value. So therefore, the baryon symmetry. So to explain the baryon symmetry of the universe, so we need new physics. So which can give us sources of the CP violation and the non-thermal equilibrium situation. Then, so I'd like to explain the electroweak baryogenesis. So in the electroweak baryogenesis, the Sakharov's condition can be satisfied by these mechanisms. So these are very similar to the baryogenesis in the star. So this figure shows a mechanism to produce the baryosymmetry via the electroweak baryogenesis. So first, when the first order phase transition occurs at the early universe, then the vacuum bubbles are nucleated at a certain time or certain temperature, and the nucleated vacuum bubble can expand. Then this vacuum bubble interact with elementary particles in the plasma, and if the CP violation exists. The CP violation exists in the interaction between the vacuum bubble wall and the plasma, then this chiral asymmetry can be produced around the vacuum bubble. And then the produced chiral asymmetry can be transferred into the baryon symmetry via the Sparrow process. And then this produced baryon density go to the inside of the vacuum bubble, and then if the spiral process is decoupled in the inside of the vacuum bubble, then the sufficient number of the baryosymmetry can be explained. So this is the outline of the electroweak baryogenesis. So what I want to emphasize here is that so in order to realize the electroweak baryogenesis, the spiral process should be decoupled after the phase transition or the inside the vacuum bubble. So this is the condition of the electroweak baryogenesis. And then if the first order phase transition occurs at the early universe, then the gravitational waves can be produced. So this figure shows the universe at the early universe. And when the first order phase transition occurs, then the vacuum bubbles are nucleated in a spiral place. And then these vacuum bubbles expand, and then the vacuum bubbles collide each other. Then the gravitational waves can be produced. And there are three sources of the gravitational waves. The first one is the collision of the vacuum bubbles. And the second one is the sound waves. And the third one is a turbulence. So these are the main sources of the gravitational waves from the first order phase transition. So it means that by observing the characteristic gravitational waves, so we may test the first order electroweak phase transition. So I will explain the detail. So in order to realize the electroweak baryogenesis, as I explained, the first order electroweak phase transition is required. So I will explain how to realize the first order electroweak phase transition. So this is the effective potential, the generic effective potential at the finite temperature system. And here we take the high temperature expansion limit. So this quadratic term gives to us potential around the origin, and this cubic term lowers the potential. And then this aquatic term lifts up the potential. Then, so the potential barrier between the false vacuum and the true vacuum can be produced. So to realize this potential, the coefficient of E plays an important role. So this figure, these are the prediction in the standard model. So as we can see, the coefficient of E can be changed by the bosonic degree of freedom. So mH is the mass of the Higgs boson, and the MW and the LZ the mass of the gauge boson. This will be. So therefore, so by adding the additional bosonic degree of freedom, so this coefficient can be large. Then the first order electroweak phase transition can be realized. And the strength of the first order electroweak phase transition is generally defined by this form. So Vn over Tn. And Tn is a temperature when the phase transition occurs, like this. And Vn is the order parameter at the Tn. So this ratio plays an important role to test the electroweak baryogenesis.
So
Yes.
I have a very nice question. So the E term, you mean that the E term triggers the first order phase transition, but not in this case, but you should add some extra scalar freedom.
Exactly, yes.
So it just means that there is no dynamical difference between the standard model and the extension of the standard model one, except for just by introducing one extra scalar. Or I mean, just if you add extra scalar degree of freedom, just the mass cubic term is just added to the E, right?
Yes.
Right? That's enough. Exactly.
So you mean that so
You said that in the standard model, only the crossover is realized and there is no crossover.
exactly, yes. Yes.
But just adding the scalar, extra scalar degree of freedom, then it turns to the crossover transition.
Yes, exactly.
It
So
just depends on the numerical value of this E.
naively, yes. Naively, yes. So yeah. So this is the prediction in the standard model, and yeah. So when we predict the dynamics of the electroweak phase transition by using the perturbative method, then the standard model predicts that the electroweak phase transition should be first order. So, however, so when we discuss the electroweak phase transition by using the lattice simulation, then the first order phase transition cannot be realized in the standard model.
Then you mean that in this effective field theory treatment, it's rather difficult to find out the standard model prefers the crossover.
So there's a limit to discuss the whether the electroweak phase transition is a first order or the or other crossover or something. So by using the perturbative method. So to show the so when we consider the new physics model, so it is not trivial. So that this model so really realize the first order electroweak transition or the or not. So yeah.
So in this case, that it means that you are not sure that really the first order phase transition occurs even if you have the extra scalar.
Yes.
If you unless you study about lattice calculation.
So therefore the perturbative analysis is a kind of the litmus. So so therefore
Sufficient condition, but not necessary.
Yes. So and then by using this effective potential, this ratio can be expressed by this form. And lambda Tn is a aquatic coupling, and E is the coefficient of the cubic.
So what is alpha p? Right.
Which one? Alpha B?
For lambda t. It's a logarithmic.
Ah, yes, this one. Yeah.
Yeah, alpha b.
Alpha is a constant. Constant.
Some constant.
Yes, constant. So actually, I forgot the expressing number. Yeah, but just a constant. Yes. So when this value is large, then the strength of the first order phase transition can be actually strong. First order electroweak transition can be strong. Okay, so next I'd like to discuss the relation between the first order electroweak phase transition and the triple Higgs boson coupling. The triple Higgs boson coupling can be calculated by using the effective potential at the zero temperature. So when we consider the extended Higgs model, then in general, this coupling can deviate from the standard model prediction like this. So when we consider the two Higgs-covered model, so in which the standard model is extended by adding additional iso-doublet scalability, then this deviation can be expressed by this formula. And the M5 is a mass of the additional Higgs boson. So in the six-doublet model, so there are three types of additional stars. And in general, these the mass of this field can be expressed by this form. And the important point is that the second term depends on the vacuum expectation. However, the first term does not depend on the vacuum expectation value.
Okay, so capital M is the value of another
If you consider such renormalizable models, I think that you can interpret the origin of capital M.
So what's the definition of capital M here?
Okay. So sorry, I did not prepare, but the definition of M is so when we consider the potential of the two-separate models, so it includes the softly G2 problem. So plus and the M is given by the
Linear combination of
yes, that's the derivation.
in the mass ion state.
まさに次です。Okay, so here the mass of the addition Higgs boson can be expressed by this formula. So we can consider two cases. The first one is that this first term is a leading in the mass of the additional Higgs boson. Then this triple Higgs boson coupling can be expressed by this formula like this. So in this case, the triple Higgs boson coupling is proportional to the inverse of the M5 square. So therefore, when we take the large M5 limit, then the deviation is getting small. So this behavior is so-called the decoupling behavior. So on the other hand, so when we consider the case where the second term is leading in the M5, then this deviation is proportional to the force power of M5. So therefore, when we take the large M5, then the triple Higgs boson coupling can significantly deviate from the standard model prediction. So this behavior is so-called the non-decoupling behavior. So this property is very interesting. And this figure shows a prediction in the triple Higgs boson coupling, the fixed-belt model with a non-decoupling. So as you can see, the triple Higgs boson coupling can deviate from the standard model prediction about a few 100%. So this is very interesting. So therefore, the non-decoupling effect is a very interesting phenomenon. So when we discussed the electroweak baryogenesis, I explained that the spiraling process should be decoupled after the phase transition. So this condition is so-called the spiraling decoupling condition. And the spiraling decoupling condition can be expressed by this formula. So this inequality means that the strength of the phase transition should be larger than unity. So if this condition is satisfied, the electroweak baryogenesis might be able to realize. So, and especially we call the first order electroweak phase transition satisfying this condition as a strongly first order electroweak phase transition. So this is the definition of the strongly first order electroweak phase transition. And by using this condition, we can discuss the constraint on the triple Higgs boson coupling in severely extended Higgs model. Because in order to realize the large Vn over Tn, so as we confirmed, the cubic term plays an important role. On the other hand, the triple Higgs boson coupling is calculated by the third derivative of the effect potential. Therefore, we naively expect that there is a correlation. So actually, in the Twix-Everett model, so by using this condition, we can discuss that the triple Higgs, we can obtain triple Higgs boson coupling should deviate from the standard model prediction about 20 or 30%.
So maybe I ask the same question.
Mhm.
So this eta,
Mhm.
so this vanishes when t equals 0.
That's it, yes.
But on the other hand, the right hand side, so it's the cubic term in the zero temperature.
Yes.
So in this sense, so they are completely independent. So in this expression.
Yes, exactly. Yes. Yeah, so this is a very naive expectation. Yeah, as you pointed out, so when we take the zero temperature limit, so this coefficient does not affect.
But you are claiming that they are actually related in some way.
Yes. So yeah. So when you calculate the coefficient and the triple Higgs boson coupling in the Twix-Everett model, so the coefficient is proportional to the cubic of the additional Higgs boson. So in the Twix-Everett model, the phi is h. That's Higgs boson. And on the other hand, the triple Higgs boson coupling, as we confirmed proportion to the body. So therefore, we expect that. So now. Yeah. Therefore, and this proportion to the V over T. Therefore, in order to realize the large V over T, and in general, the triple Higgs boson coupling is also.
So is this special for this Twix-Everett model, or do you think it's very general?
Yeah, actually, this is not the general. So when we consider severely extended Higgs model, so this naive expectation, so is not valid. So this is a result only in the Twix-Everett. So as we confirmed, the triple Higgs boson coupling should vary from the standard model prediction about Q 10%. And such large deviation is required to realize strongly first order electroweak phase transition. So therefore, we expect that the non-decoupling effect is very important to satisfy the spiral decoupling condition. And then I will review the current and future constraint on the triplet exposure coupling. And this is the current constraint from the LHC result. So as we can see, the constraint on the triplet exposure coupling is very weak. So therefore, we can realize such large deviation in the Pareto state. And this figure shows the future constraint on the triplet exposure coupling. For example, at the high luminosity LHC, this coupling can be measured by the 50% accuracy. And if the electron colliders with a 1 TeV center mass energy, then this coupling can be measured by the 10% accuracy. So therefore, to test the electroweak phase transition, so we need a future correct. So next, I'd like to explain the new EFT framework. So far, we have discussed the dynamics of the electroweak phase transition in severe extended Higgs model. However, if possible, so we want to extract the model independent properties of the electroweak phase transition. Then, so we need the effective field theory, so which can appropriately describe the first order electroweak phase transition. And then, so in general, so to explain the phenomena beyond the standard model, so we often assume the new physics whose scale is higher than the typical electroweak scale. And the effects from such heavy new particles can be described by using the EFT framework. So there are two famous EFT frameworks. The first one is a standard model effective field theory, which is solved with SMEC. And the second one is Higgs. So then I'd like to explain what is the SMEC, standard model effective field theory. So let's consider the Higgs potential in the SMEC, so up to the dimension 6 operator. So in the standard model, so the Higgs potential only has two terms, like this. Then so let's consider the new particle, so which interact with the Higgs boson, and then so we can consider such diagram, for example. And here we assume that the mass of the new particle X should be heavier than the electroweak scale. Then, so according to the uncertainty principle, so we expect that this such heavy new particle only propagate a short length. Therefore, so we can shrink this loop like this. So therefore, it means that so by adding the higher dimensional operator to the Higgs potential, so we can describe the new physics effect to the standard. So this is the main concept for the standard model effect field theory. In the SMEC, the standard model is extended by adding the higher dimensional operators. And the SMEC is very useful. So when we discuss the model independent phenomenology. So I'd like to explain what is the nearly aligned Higgs. So in this talk, so we are interested in the dynamics of the electroweak phase transition. Therefore, so we only focus on the potential part in the nearly aligned Higgs. So this is the Lagrange of the nearly aligned Higgs. And the first term is the Lagrange in the standard model. And in this EFT, so the new physics effect can be described by adding these operators. So the most important point is that this potential includes a logarithmic structure, so which is similar to the Coleman-Weinberg potential. And this potential have the one form factor m squared. And in this talk, so for simplicity, we assume that this form factor can be expressed by this form. So this form is very similar to the mass of the additional Higgs boson in the Twix cell. Then, so we can consider when we consider the decoupling region, it means that this first term is leading in this m squared. Then, so we can expand the logarithmic part in terms of the phi. Then, so we can obtain like this, we can obtain the dimension 6 operator like this. So it means that the SMACT is a good approximation when we consider the decoupling region. So how?
What's the meaning of nearly aligned here?
So yeah, so when we discuss the electroweak phase transition, the nearly aligned is not important, but I will explain. So this is the generic Lagrangian is a nearly aligned EFT. And this EFT can predict the non-alignment case. The non-alignment with the kappa V and kappa A can deviate from the standard model prediction. So this is the meaning of the nearly aligned.
Kappa F is the Yukawa, right?
Yes, Higgs to the Yukawa. Higgs to
So
the
in the nearly aligned case,
Mhm.
so you mean kappa V and kappa A is almost the same.
Almost same.
So could you again explain the meaning of nearly aligned?
In general, so according to the LHC result, so the LHC requires that the ratio of the kappa and the ratio of the Higgs to gauge boson coupling and fermion coupling are the unity.
Yeah.
So according to the LHC result.
But
But in the
case.
yes, exactly.
Yeah.
So, and yeah, in the standard model, the observation facts can be easily explained. So, however, when we consider the new physics model, in general, this kappa V and kappa A can deviate from the standard model prediction.
Yes.
And this EFT can describe such new physics with a non-alignment. So this is the reason why we call this EFT as a nearly aligned.
So here nearly aligned means kappa V and kappa A is almost unity.
Exactly. Yes.
Okay.
Yes.
And the extra boson mass can be like
So-
extra explosions.
Uh-huh.
For example, Twix double model.
Uh-huh.
Actually, there is some distinction between the alignment limit and the coupling limit.
Exactly. Yes.
So the alignment limit, mixing angle is quite suppressed, but instead, but extra explosion is in the light. The coupling limit means that when the extra explosion is very heavy, it's out from the theory.
Yes.
But in your case, you are saying that the alignment is kind of alignment limit.
Mhm.
And the extra explosion,
Can be light. Yes. Yeah.
will give the decoupling.
Yes. Exactly. Yes.
So as you already said, it seems so nearly aligned is not important when you consider this kind of potential.
Yes. Yes.
This
So
is
when,
just a Coleman-Weinberg potential.
yes. Yeah. When we discuss the dynamics of the first order phase transition, so the nearly aligned is not important in general. This potential part is important. Okay. So we confirm the decoupling. What happened when we consider the decoupling? And then, so in the non-decoupling region, so which means that this second term is leading the mass of the addition exposure. Then, so we cannot expand the logarithmic in terms of the phi because so this second term is very large. So it means that so the SMACT may not be good in the non-decoupling region. So therefore, by using this EFT, so we can discuss, so we may discuss the phenomenology in the non-decoupling region. And in this EFT, so there are three parameters. The first one is capital lambda, which corresponds to the mass of the new particles. And the second one is kappa zero. Kappa zero is the degree of freedom of the new particles. And third one is R. So R is defined by this form. And we call R as a non-decouplingness. So what is the meaning of the non-decouplingness? So it means that when we consider the when we take the R when we take R as around 0, then the decoupling case can be realized. On the other hand, so when we take the R as a almost unity, then the non-decoupling case can be realized in this EFT. So what is the meaning? So this figure shows the property of the new particle group. This figure shows the groups of the new particles. In serial parts, the decoupling property, decoupling EFT can be described. In serial parts, non-decoupling EFT can describe the such new Higgs, new physics. And in the nearly aligned Higgs EFT, by changing the parameter R, so this EFT can describe both cases. So this is the interesting point of the nearly aligned Higgs EFT. And so far, so we have discussed the nearly aligned Higgs EFT at the 0 temperature. So, however, when we discuss the dynamics of the electroweak phase transition, so of course we should take into account the thermal correction. And we extended this EFT to the final temperature system. And this is the effective potential at the final temperature in the nearly aligned Higgs EFT. And the first term is potential in the standard mode at the final temperature system. And the second one is correction to the Higgs potential from the new particles at the 0 temperature. So this is 0 temperature. And third term is thermal correction from the new physics. And the JBSM is defined by this form. And by using this potential, we can discuss electroweak phase transition. This figure shows the prediction in the nearly aligned EFT, and horizontal axis is R. R is a non-decouplingness, and when we take the small, if the value of R is small, then decoupling situation can be realized. On the other hand, R is around unity, then non-decoupling case can be realized. And the vertical axis is represents ratio of the Vn over Tn. So Tn is a temperature starting the phase transition, and Vn is a bottom expectation at the Tn. And the red line is the prediction in the near aligned EFT, and which is very consistent with the result in the standard mode with a single. Therefore, the near aligned EFT can well describe the phase transition in several new physics mode. And these blue lines are the prediction in the SMEC up to the dimension 6, up to the dimension 8, and the dimension 10 of eta. So as we can see, so there's a discrepancy between the discrepancy in the Vn by Tn between the SMEC and the nearly aligned EFT. So it means that the SMEC may not be appropriate when we discuss the strongly fast order electroweak phase transition. The condition of the strongly fast order electroweak phase transition is that the Vn over Tn should be larger than unity. And so once we define the effective potential, so we can discuss the prediction on the gravitational waves. And we actually, so we have analyzed the prediction of the gravitational waves and in the nearly analytic safety. And these colored line are the prediction in the nearly analytic safety with a severe parameter set. So as we can see, so the graph. So as we can see, at the future space-based interferometers like the PD of this Lisa HSC, and so we may explore the dynamics of the first-order electroweak phase transition. So therefore, the gravitational wave observation is useful to test the first-order electroweak phase transition.
So in this book, so each gravitational wave is
Sound wave, yes. Yeah, peak structure is almost determined by the sound wave. So finally, so I'd like to explain the relation between the electroweak phase transition and the primordial. So this is the main part of my talk. So first, I have to explain what is a primordial black hole. The primordial black hole are the black hole formed before the star formation. So not after the star formation. And to realize the PBH formations, so the large energy density fluctuation should be realized at the early universe. And also there is a condition for the PBH formation. This is a condition of the PBH formation. And the Lobach is the energy density, the average energy density in a whole of a universe. Okay. So the Lobach corresponds to this. And the rho over is the energy density in the overdensity region. And if the energy density is equality, then such overdensity region can gravitationally collapse into the primordial black hole. So this is the PBH formation mechanism, generic PBH formation mechanism. And interestingly, so this PBH formation condition can be satisfied when the first order phase transition occurs at the early universe. Therefore, so it means that the primordial black hole might be produced by the first order phase transition. So next, I'd like to explain how to produce the PBH by using the first order phase transition. And here we focus on this mechanism. So this figure shows a time evolution of our universe. And at a certain time, so we call time as a T phase. And then, so in severe place, the phase transition is already occurred. And this gray region, in this gray region, the phase transition is already occurred. And on the other hand, in this white region, the phase transition is not occurred. And our universe, the temperature of our universe cools down, then the almost space experience the phase transition, as shown in this figure. However, so there is a possibility that the phase transition does not occur in a whole horizon. So there is a possibility which can realize such situation. And as the universe the temperature of our universe is getting low, then the large energy density fluctuation can be realized between this symmetry unbroken region and symmetry broken region. Because in this white region, the vacuum energy is very large. Because in the pulse vacuum, which corresponds to this white region, then the potential barrier is there is a this difference between potential. So therefore, so if such situation is realized, then the large energy density fluctuation can be realized between the white region and the gray region. And if the density fluctuation satisfies this inequality, then this region can collapse into the primordial. So this is a PBH formation mechanism by using the first order explanation. So, and when we discuss the PBH formation, the criterion, the criterion of the PBH formation is very important. So in this talk, so we take delta C as a 0.45. So this value is often used when we discuss the PBH formation. Therefore, so we take this value. It's following. And the property of the PBH produced by the first order electroweak phase transition is already discussed in the within the framework of the SMEC. However, so as I explained, the SMEC may not be appropriate when we discuss the strongly first order electroweak phase transition. Therefore, in this talk, so we discuss the PBH formation in the nearly aligned EFT instead of the SMEC. And the typical mass of the PBH produced by the electroweak phase transition is around this value. So, and this figure shows the current constraint of the PBH. And the horizontal axis is the mass of the PBH in the solar mass unit. And vertical axis is a fraction of the primordial black hole. The fraction is defined by the energy density of the PBH and the dark. So if the PBH with this mass are observed, then so we may test the first order electroweak phase transition like this. And the most important point is that the primordial black hole within this mass region is already constrained by the microlensing observation, like the Subaru hypersupreme curve OGLE. So it means that by using this result, we can discuss the constraint on the new physics. So this is very interesting. And in the near future, the severe improved microlensing observation will start, like the prime and Roma. And once these experiments will be ongoing, then the fraction of the primordial black hole will be constrained by the 10 to the minus 4 this. Therefore, so if these experiments start, so we can discuss the more wide. We can discuss the constraint on the new physics.
So those PBH masses calculated with the assumption that the electric edge transition successfully produced the baryon symmetry.
No, so this value is almost finished, almost determined by the Hubble horizon.
But it should be, there should be some kind of percentage instead of crossover. But you said that in the standard model, just crossover.
Yes, in the standard.
Primordial black hole.
Yes.
And it seems to me that the primordial black hole itself should be sensitive to the some kind of extra scalar freedom.
Exactly. Yes.
Physics.
Yes, exactly. So yeah, so that is an important point. So it means that by using the primordial black hole, so primordial black hole observation, we can discuss constraint on the property of the new particle, new additional scalar. That is very important.
Okay, I have this one.
Which one?
So in this left photo,
This one. Okay.
yeah. So what do you what's the parameter?
So this
Yeah, parameter do you change?
yeah, so this is an example. So it's
Yeah, I know. That's the example.
show the example. So in this plot, we take the kappa 0 as a file, and we consider the non-decoupling case. And by changing the parameter, lambda is correspond to the mass of the new particle. So by changing the lambda, so the fraction is drastically changed.
It's very sensitive.
Very sensitive, yes, exactly. So
It's calculated based on the SNEFT.
no, so this is based on the nearly aligned Higgs.
Yeah, yeah.
Yes. So yeah, then the fraction is very sensitive to the model parameter. And yes, and so finally, I want to explain and the final result. So the main question of this talk is that how can we test the first order electroweak phase transition? And we have confirmed that there are three options. The first one is the electroweak boson coupling measurement. The second one is gravitational wave observations, and the primordial black hole observation. So this figure shows the parameter region, so which can be explored by each experiment. And in this figure also, of course, we assume the nearly aligned Higgs EFT, and we take kappa 0 as 1. And the horizontal axis indicates the R, and the vertical axis is the mass of the new particle. And this colored region, the spiral decoupling condition, which can be expressed by this inequality, can be satisfied. Therefore, the new physics model in this colored region, the electroweak baryogenesis might be able to realize. And the gravitational observation like this cycle can explore the blue and orange region respectively. And in the red region, so it seems like a line. However, this is a region. And in this red region, the primordial black hole can explore this region. And for this green region, unfortunately, this region cannot be explored by the gravitational wave observation and the PBH observation. So, however, this region can be explored by the future Correlate experiments, and especially the Correlate experiments, which can measure triple Higgs boson coupling precisely. So these black contours indicates the prediction of the triple Higgs boson coupling. From the bottom, the 20% deviation, the 50% deviation, 100 and 200. So as we can see, if we observe the large deviation in the triple Higgs boson coupling, so this green region can be explored by the Correlate experiments. So therefore, the first order electroweak phase transition can be explored by using the PBH observation in addition to the gravitational wave observations and Correlate experiments. So this is the main result. And so in addition to, we have confirmed that the parameter region, so which can be explored by the PBH observation. And this figure shows the parameter region where the sufficient amount of the primordial black hole can be produced by the first order electroweak phase transition. So as we can see, the white parameter region in new physics model might be explored by the current of future PBH observation. This is also the main result that works. And finally, so this is this figure shows the timeline of the current and the future experiment. So in the 2000 around the 2030, the gravitational wave observation will start, and in the middle of the 2030s, the experiments will start, which can explore the triple Higgs boson coupling. So in this talk, so we discussed the PBH observation. And what I want to emphasize here is that the primordial black hole observation is ongoing. And in the near future, so we can obtain the more improved result. So this is very important. Okay, so let's summarize. And in this talk, so we have proposed a nearly aligned EFT, so which can appropriately describe first order electroweak phase. And we discuss the strongly first order electroweak phase transition can be explored by the current and the future PBH observation. So especially the microlensing observation, like the Subaru HSC, OGLE prime, and Roman test. And we have confirmed that the wide parameter region may be explored by the PBH observation. So what I want to emphasize here is that by using the quadratic experiments, gravitational wave observation, and PBH observation, so the dynamics of the electroweak phase transition is thoroughly explored. Okay, so that's all. Thank you very much.
Thank you very much for the nice talk. Any question?
How do you detect PBH?
Sorry.
How do you detect PBH?
So for the microlensing observation, so we observe the we use a gravitational lensing effect in the microlensing effect.
Okay, so I think my question is, how do you distinguish how can you tell a black hole is a primordial black hole or not?
Yeah, that's a very good question. So in general, so if the black holes produced, okay, so if the black holes are produced by after the star formation, the typical mass of the black hole is around the solar mass. However, the primordial black hole can take the more small value. Yeah.
Very robust.
Yeah. So in general, so strictly speaking,
So widely accepted right?
yeah. So yeah, strictly speaking, so for example, yeah. So we can produce the primordial black hole with around the solar mass. For example, if the QCD phase transition is a first order, then it predicts that the primordial black hole mass is around the solar mass. So because this PBH mass depends on the Hubble horizon, therefore if the typical phase transition temperature is changed, then we can realize such the star formation like black hole. So therefore as you pointed out, it is difficult to distinguish the primordial black hole and the black holes formed after the star formation. I think that's it.
Electrical representation is less, right? And high, but the QCD can be. But
The horizon is
Expand. So yeah.
different size of
it's high electric representation.
electric input.
Yes, yes.
Mhm.
And for example, got phase transition related primordial black hole.
Yes, I think so. Yeah, I think that we can get more light black hole.
And this micro sensing can sensitive up to 10.5.
Sorry?
So what's the sensitivity for this detection? So I think they did deflecting related to the mass, right? Page. So
It is too light.
I think so. So the rendering effect, you can decide the mass of the PBH, right?
Yes. Yes. Yeah.
In this slide, you show the PBH fraction within NaH, CEFT, or SMF.
Sorry.
So this red here.
Uh-huh.
Is that from SMEFT or nearly aligned Higgs EFT.
So
What, the
both,
same?
both, yes, because
The same?
yes, almost same. Because this mass is already it's almost determined Hubble horizon at the phase transition, when the phase transition occurs. And of course, the electroweak phase transition it should be occurred around the 100 GB scale. Therefore, how should I say? So there's no difference between the SNAP and the nearly analytic. The mass is almost the same.
And I don't think you show the details how you calculate
A fraction.
PBH.
Okay, so that's the important question. Yeah, I will explain. So, oh. Okay, so yeah, okay. So this slide explains how to obtain the PBH function. And the first, we should evaluate the possibility that such a symmetry unbroken symmetry is not broken in a Hubble horizon. So this possibility can be determined by the transition rate of the phase transition. Yeah. Oh. Yeah. So by using the transition rate, so we can calculate the possibility, and then so we evaluate the. Okay, so I should say so. So this is the current approach horizon, and we compare the. So this is a Hubble parameter when Hubble scale when the phase transition occurs. So therefore, we can obtain the number. So we can determine the number of the Hubble horizon when the phase transition occurs. And yeah, if the number density and the number obtained, then so we should. P is a possibility. The symmetry is not broken in a whole Hubble function. So then we can obtain the fraction.
And P is to be calculated from the first principle, right?
Sorry?
Some probability
Uh-huh.
distribution domains or something like that. Then it should be calculated with the framework of theory or
In the mechanism, so the P can be determined by the tunneling rate of the first order precision. If we take this form, so the possibility can be easily calculated.
you show the plot that which is very sensitive to the lambda value. F, yeah,
So in
Yeah,
general,
yeah.
the fraction can be
that's right. FPBH is very sensitive to the lambda here.
very sensitive, yes.
Yeah, but in this figure, I cannot see the origin of such kind of. How lambda actually play the role in the calculation of that?
Okay, so I think that this figure. Okay. Okay, so I think this result is useful. So in order to realize the first order phase transition, so we should create the potential barrier, and this potential barrier is proportional to the Vn over Ta. So the potential barrier is proportional to the cubic of the Vn over T. This. And so this proportional to the cubic of the E3, and this E is proportional to the quantic of the lambda. Yeah, so this is the reason. So mainly it's nice.
Any other question?
And primordial black hole, which is generated from the QCD page transition, still surviving or excluded by observation? Mass of almost solar mass black holes.
If the QCD phase transition is the first order, but
Yeah,
in the standard model, QCD phase transition is a crossover. I think
Yeah, I
therefore,
understand.
yeah, we cannot realize
I
image
see.
formation in the standard.
So,
Yeah, even if we consider the new physics with extended Higgs model, extended Higgs structures, but I think that the QCD phase transition is not changed.
people usually people do not take it seriously.
I think so. Yeah.
First order phase transition QCD.
Mhm.
Actually, I heard from lattice people that they are quite confident that QCD phase transition is crossover. QCD phase transition is not crossover, but no, that's the crossover.
It's crossover, yes.
Lattice people.
Does it? All the stuff. Oh, I'm sorry, but I think you explained it, but you explain again, what is the NA nearly aligned? What do you mean by nearly aligned?
The meaning of nearly aligned is that so in this EFT, so this is the generic Lagrangian of the nearly aligned EFT, and this EFT can explain the new physics with a non-alignment case, like as shown in this figure. So the coupling of the Higgs between the Higgs and the boson or fermion can deviate from the standard model prediction. Yeah, according to the current.
So I mean, in this parameterization, I mean, there is no nearly aligned or whatever. It's just general parameterization.
So I didn't get your point.
If you just adopt Higgs EFT, then this is just effective Lagrangian.
Exactly. Yes. So
So what do you mean by nearly aligned?
yeah.
Kappa close to one? Or what do you mean by?
So yeah. So yeah, as you pointed out, so actually so this part is the same as the ordinary Higgs EFT.
Yeah.
So this part is not special. It's a nearly aligned Higgs EFT.
Yeah.
Yeah. The main difference is that the main difference is that in the nearly aligned Higgs EFT, so we take the this potential form. Yes. Yes, this is the difference between the ordinary Higgs EFT and the nearly aligned Higgs EFT.
So so Higgs EFT, so your definition of nearly aligned Higgs EFT is that you include one effective potential?
In the Higgs potential, yes.
And the LSM,
Yes, this is the
is the normalized part or is the normalizable standard model part or is it still have a Higgs EFT? So when LSM is a Higgs EFT?
no, so this is just the standard model Lagrangian.
So then, where are the C-level contribution of new physics?
Okay, so yeah. So the serial parts are written in Japanese. So okay, so this is the Lagrangian.
Plus BSM.
Yes, so this is the generic Lagrangian of the area aligned Higgs. So, yeah. So the BSM part can be described by this form. So the LBSM includes the potential corrections and severe correction to the kinetic term of the Higgs boson or Yukawa interaction.
So, from your notation, you have a psi which is 1/16 pi square. I think that's from loop factor.
Yes, yeah, we are assuming that the new physics effect only appears via the loop effects.
So my question is, when you integrate the heavy particle, this your BSM Lagrangian includes only the
Loop effect.
new particle in the loop.
Yes,
But
exactly.
new particle can be in the propagate in the tree level.
Exactly. So
And you
therefore,
can integrate out.
yeah.
So where these effects appear in your?
So in this EFT, so we did not take into account such effect. So, so therefore, so as you pointed out, so there is a possibility which includes the new physics effect appears at the tree level. So therefore, so in order to describe such model, we should extend this EFT. So in this EFT, we assume that the new particle effects only appears via the loop effect. The new particle only appears in the loop. So this is the assumption of this EFT.
So your NA Higgs EFT can be a good approximation for testable model.
Yes. Because, yeah. So when we discuss especially when we discuss the dynamics of the electroweak phase transition, so this EFT is a very good consistent.
You show this potential.
Yes.
You show this one.
Potential. So this one? This one?
Yeah. So do you apply? So do you assume that your NA EFT applies in the whole region, both for first vector and the two vector?
Yes, we applied the both sides.
And this energy difference between first and two vector is related with low over density.
Yes, it's related to the low over density. Yes, exactly.
Any other question? If not, let's thank speaker again. Thank you very much.